Welcome to the debate.
It's good to be back.
It is a really remarkable time to be having this conversation. We just passed a huge milestone. 2024 was the 200th anniversary of the naming of Megalosaurus. That was it. That was the moment we first put a scientific name on one of these terrible lizards.
2 centuries. It's incredible. And in that time, we've completely rewritten the ending of the story, haven't we? We went from dinosaurs being these, lumbering, cold-blooded failures wiped out by a rock to realizing they aren't extinct at all.
Exactly. They are still here. I mean, we are literally surrounded by them, about 11,000 species of birds alive today. And this is the key. While the fact that birds are dinosaurs is settled science now, the mechanics of that transition, the specific how, that remains one of the most contentious battlegrounds in all of paleontology.
It really is. We're not arguing about the family tree today. We are arguing about physics. We're talking about gravity, we're talking about anatomy, and the precise sequence of adaptations that turned a ground-based predator into, an avian skymaster.
Precisely. So the question for us today is the origin of flight. I'll be representing the consensus view, often called the ground-up or cursorial theory. My position is that the bird blueprint was essentially assembled on the ground. These were Maniraptor and theropods, active, running predators that just gradually accumulated bird-like traits, things like feathers, air sacs, hollow bones, all while living firmly on the earth. Flight was simply the final, logical extension of a running lifestyle.
And see, that's where I have to step in. I'm here to argue for the trees down, or arboreal theory. And my position is that the physics of taking off from a standstill on the ground is it's an almost insurmountable hurdle for a proto-bird. When I look at the developmental complexity, the huge gaps in the fossil record, like with tail reduction, and the clear evidence of four-winged gliders, I see a transition that had to be arboreal. It wasn't some smooth run into the air. It was a chaotic, gravity-assisted experiment from the canopy down.
Well, let's start by grounding this in the phylogeny, the family tree, because that lineage is just undeniable. We're looking at a clear progression. It started with Thomas Henry Huxley back in the 19th century, but it was really John Ostrom's work on Deinonychus in the 60s that cemented the skeletal similarities.
Oh, I don't dispute the skeletal similarities. The hardware is clearly dinosaurian. No argument there.
But just consider the extent of it. We're talking about the wrist that snaps sideways, the semilunic carpal. We're talking about the shoulder, the hip. I mean, we now know that the entire avian package was put together on the ground long before flight was ever a factor. We have clear evidence of flow-through respiratory systems, air sacs, in non-avian theropods like Manjungasaurus.
The high-efficiency breathing system, right.
Exactly. That system, which is crucial for high-energy flight in modern birds, it evolved in terrestrial predators, probably to, help them run down prey without getting winded. We found medullary bone in a T-Rex femur, a tissue female birds use for eggshell calcium, and, of course, the big one, feathers. Sinosarcpteryx, Caudipteryx, they prove that feathers evolved for insulation or for display in animals that were 100% ground-dwelling. Flight didn't create these features. It just co-opted them.
Okay, and I see why you emphasize the phylogeny. Those shared traits are, indisputable evidence of ancestry. But I am just not convinced by that line of reasoning when we're trying to explain the function of flight. You're describing an animal on the ground, accumulating all these parts, but then you're asking us to believe that this runner, fighting gravity every step of the way, somehow generated enough lift to become airborne. That is an energetic nightmare.
A challenge, yes, but not a nightmare.
It is physically inefficient. I come at this from a different angle. If you look at the small, feathered dinosaurs right at that transition point, I'm talking about animals like Microraptor or the Scansoriopterigids. You see adaptations that make absolutely no sense for a ground runner. Microraptor had long, asymmetric flight feathers on its hind legs. It was
the four-winged condition. It's certainly fascinating.
Ground-up hypothesis. A ground runner with long flight feathers on its feet would be tripping over itself constantly. It's like trying to run a marathon in, snowshoes. These animals scream that an arboreal gliding stage was essential. Gravity works for you when you jump from a tree, not against you.
And that brings us right to our first major point of contention, the mechanism for the origin of flight. You mentioned the tripping hazard of leg feathers, but let me offer you a different perspective. We have modern analogs for this. Young birds, like chuka chicks, for example, they use a behavior called wing-assisted incline running, WARE.
I'm familiar with the where concept, yes.
It is a critical piece of this puzzle. When these little chicks need to escape a predator, they can't fly it, so instead they flap their developing wings to run up steep slopes, sometimes even vertical tree trunks.
But they aren't flying.
No, they're generating downforce. They're pushing themselves into the surface to get more traction. It works like a spoiler on a race car. This fits the ground-up model perfectly. You don't need to defy gravity right away. You just need to manipulate traction to scramble away from danger. True flight can emerge later as the muscles strengthen and the stroke angle changes.
That's a compelling theory, I'll grant you, but have you looked at the anatomical constraints in the earliest birds? Wire isn't just flapping around. It requires a very specific mechanical stroke. In modern birds, that downforce is generated by a swift, powerful upstroke of the wing. To do that, they use a whole rope and pulley system in the shoulder called the supracoracoideus.
And early birds lacked that specific arrangement, I know.
They didn't just lack the arrangement, they lacked the pulley entirely. Archaeopteryx did not have it. The early stem birds didn't have it. And without that pulley, they physically could not produce the swift, high-frequency upstroke you need for wire. Anatomically, these early birds look much more like gliders, where the upstroke is less critical than just having a static lifting surface.
I would frame that differently. I mean, Microraptor is a striking fossil, no doubt, but it might just represent a specific offshoot, a convergent experiment in flight, rather than the main ancestral state for all birds. Just because one lineage went up into the trees and developed four wings doesn't mean the main line of avian evolution did.
But it's not just Microraptor. Look at Anchiornis, look at Scansoriopteryx with its crazy elongated fingers for climbing. These are animals built for a three-dimensional arboreal world.
But if we look at Archaeopteryx, recent studies on its wing bone geometry suggest it was capable of active flight, even if its stroke was different from a modern pigeon. The lack of a modern supracoracoideus pulley doesn't rule out a terrestrial takeoff. It just means the mechanics were different. We see roadrunner-style tracks in the Cretaceous. We see a lineage of runners. To suggest they all had to climb trees to learn to fly, it just ignores that their anatomy, their long legs, their hip structure, is overwhelmingly cursorial.
Cursorial doesn't explain the sudden shifts we see in other systems, though. And this brings me to one of the biggest problems with the gradualist ground-up view, the tail.
The transition from the long reptilian tail to the short pygostyle?
Exactly. In the ground-up story, this is always painted as this slow, gradual reduction to improve flight balance. You lose a vertebra here, another there, until you end up with the short Pope's nose of a modern chicken. But the fossil record tells a completely different story. As noted in the review by Rashid and his colleagues, what we actually see is a sudden appearance of short-tailed birds.
Well, gaps in the fossil record are common. We shouldn't mistake an absence of evidence for evidence of absence.
But this might not just be a preservation gap. Rashid and his team highlight that tail truncation in lab mice is often caused by these pleiotropic effects from mutations in the notch and wind signaling pathways. These are genetic accidents, mutations that cause fused vertebrae, like a pygostyle, that can happen abruptly. This implies a rapid mutation-driven shift, a saltation, not a slow whittling away by natural selection.
I'm not really convinced by that line of reasoning because it creates a kind of false dichotomy. Genetic shifts can be rapid. Yes, a mutation happens in a single generation, but their retention is still driven by selection. So even if the tail loss was sudden, due to some notch pathway mutation, it happened within a lineage that was already adapting for aerial balance.
But that changes the whole narrative from adaptation for flight to adaptation to a mutation. It's like you're reacting to a broken body part.
Not necessarily. Look at Jeholernus. It's a perfect example of the mosaic nature of this whole transition. It had a long, primitive tail, but it also had modern, powerful wings. It was flying just fine with a long tail. This suggests that losing the tail wasn't the spark that created flight, but a refinement that happened later. The shift from a long counterbalance for running to a pygostyle for supporting a feather fan.
It aligns perfectly with the shift from running to flying.
Jehoranus actually supports my point about mosaic evolution. You have a bird that's modern in the wings but ancient in the tail. It shows these systems, flight, tail, brain, they were all evolving at different rates, often disconnected from each other. The ground-up theory tends to smooth all this out into one linear progression, but the reality was likely a messy series of experimental forms, and many of them were probably dead ends.
Well, speaking of success and dead ends, we have to talk about the brain. For a long time, the consensus was that the avian brain, hyperinflated, capable of rapid 3D processing, was a prerequisite for flight. You need a supercomputer to navigate 3D space.
That was the consensus. But here we are, 200 years after Megalosaurus, still finding things that just completely break our models.
And I assume you're referring to the recent work by Field and others on brain evolution?
I am. The discovery of Novolornis is a total paradigm shift. Here you have an enantiornithin bird, a capable flyer, totally dominant in the Cretaceous, and its skull geometry looks remarkably like a modern bird. But when you look inside, at the endocast, the brain is intermediate. It has a smaller cerebellum than modern birds.
It is a fascinating mosaic, I'll agree. Novolornis shows that the modern skull shape evolved before the modern brain shape.
But it proves something much more damaging to the whole flight creates brains hypothesis. If Novolornis was a capable flyer, which its skeleton says it was, but it lacked the fully modern flight-ready brain, then the modern bird brain is not a prerequisite for powered flight. Flight came first. The cognitive explosion came later.
I would interpret that a bit differently. I think Novolornis shows there are multiple ways to build a flying brain. It had a cerebrum that was larger than Archaeopteryx, but smaller than modern birds. It suggests that the cognitive demands of flight did drive brain expansion, but it was a stepwise process. The modern brain of crown birds with that massive telencephalon might be linked to other things, maybe complex social behavior or advanced foraging, not just staying airborne.
Or perhaps it suggests that the ground-up model, which relies on this whole suite of traits evolving together for flight, is just too tidy. We see flight without the modern brain. We see feathers without flight. We see long tails with active wings. It is a scramble of features.
Let's touch on those feathers again. You said earlier that feathers on the legs support the arboreal theory, but we have to look at the origin of the feathers themselves. We now have definitive proof, thanks to melanosome analysis, that early feathers were colored.
The work on Anchiornis, yes, undeniable. We know what color it was.
Exactly. Anchiornis had a red crest, like a woodpecker, spangled black and white feathers on its limbs. This tells us the primary driver for feather evolution was probably display, sexual selection, or insulation. Flight was an exaptation, a secondary co-option of a pre-existing structure.
And I agree that feathers evolved for display, but that actually weakens the cursorial argument.
How so?
Well, picture a ground-dwelling runner. If you evolve long, complex display feathers on your hind legs, like we see in Microraptor and Anchiornis, you are creating a massive liability. You're creating drag, you are tripping yourself up. However, if you are an arboreal animal, displaying from the branches, those long leg feathers aren't a hindrance at all. And if you happen to fall, these suddenly become lift surfaces. A trees-down model seamlessly transitions a display structure into a gliding structure. The ground-up model has to explain why a runner would evolve leg feathers that make running harder.
That presumes the leg feathers were as extensive in the terrestrial ancestors as they were in Microraptor. It's just as possible that the four-winged morphology is a specialized adaptation for gliding that evolved within one specific lineage, not the ancestral state for all birds. The ancestors were likely displaying, yes, but maybe with crests and tail fans, not necessarily leg wings.
We're picking at specific fossils here, but there's a technical hurdle we haven't touched on. The old band argument. Birds are not dinosaurs.
I thought we agreed that they are.
We do, but the old ornithological objection about digit homology is still a thorn in the side of the cursorial theory. It's the thumb crisis.
The counting problem.
Right. Theropod dinosaurs have digits 1, 2, 3, thumb, index, middle.
But embryological studies of birds have traditionally identified their digits as 2, 3, 4. So if birds are dinosaurs, how do you explain losing the thumb and re-evolving the fourth finger?
And that has been a real sticking point for decades, I admit. But recent developmental biology combined with new fossils has largely resolved it. We have the frame shift hypothesis.
The idea that the gene expression just shifted position?
Exactly. It's a homeotic shift. The condensation of the digits during development shifted, so the digit in position 2 takes on the identity of digit 1. It's like moving the house numbers on a street. But we also have hard fossil evidence now. You just have to look at Limosaurus.
The ceratosaur from China. Right.
Yes, it shows lateral digit reduction. It actually reduced its first digit. It shows that digit reduction is plastic in theropods. The hand problem really isn't a problem anymore. It's a great example of how developmental biology is confirming the paleontological consensus.
I'll admit Limosaurus is a compelling piece of evidence for the frame shift. But it just highlights my broader point. We constantly have to invoke these complex developmental shifts, frame shifts in hands, pleiotropic mutations in tails, to make the ground-up theory work. The arboreal theory, relying on gravity and gliding, just feels mechanically simpler even if the fossil record is patchier. You climb up, you jump off. Gravity does most of the work.
Simpler, perhaps, but it's far less supported by the sheer weight of the phylogenetic evidence. When we look at the big picture, from Archaeopteryx to Ichthyornis, we see a clear, undeniable lineage. We see the gradual assembly of the bird. First, the bones, the hollow, pneumatized skeleton, then the air sacs, then the feathers, then the flight mechanics. The ground-up theory remains the most robust because it aligns perfectly with the predatory cursorial ancestry of the theropods. They were running predators. Flight just gave them a new dimension to hunt in.
And yet the mechanics are still messy. The trees-down theory better explains the initial transition from a gravity-bound animal to a glider. The energy barrier is just so much lower. In fossils like Nava orniths, the genetic studies on tail loss, they show that evolution was not a straight line. It was a series of rapid shifts, mosaic experiments, and convergent evolutions. I mean, we see independent losses of flight in multiple dinosaur lineages. Why couldn't there be independent gains of flight, or at least gliding?
That is a fair point. Evolution is rarely a straight line. It's a bush. You're right, branching in all directions.
We also have to acknowledge that our definitions are fundamentally arbitrary. We argue about, when did it become a bird? But biology is a continuum. A velociraptor didn't just wake up one day and decide it wanted to be a chicken.
Absolutely. And I think both perspectives highlight that we are living in a true golden age of discovery. 200 years after megalosaurs, we aren't just looking at bones anymore. We are looking at soft tissue, at brain evolution, at the genetic pathways themselves.
We're moving from asking what happened to trying to understand how it felt to be a dinosaur, taking that first leap into the air. Whether it was a leap from a branch or a jump from the ground, it absolutely changed the world.
Indeed, it did. And as new fossils like Nava ornis continue to fill in the gaps, I suspect we'll find the truth probably borrows a little from both of our positions.
But until then, I'll keep looking to the trees.
And I'll keep my eyes on the ground. Thank you for joining us on The Debate.